Good morning.
Morning, sir.
Good morning.
Good morning, sir.
Good morning. Let us start. And today we'll discuss Bell-Coleman cycle, which is also called the air refrigeration cycle, or the system is called air refrigeration system, because in this case the working fluid is air. That means air is the refrigerant. Generally, for refrigeration we have to use some special fluids, but in this refrigeration system the working fluid refrigerant is air, used in aircraft refrigeration system. And in the last class also we just mentioned that a Bell-Coleman or air refrigeration system consists of one compressor, one cooler, one expander, and the main unit is the refrigerator. Okay, we will simply discuss all the components and also the cycle involved in the Bell-Coleman cycle. And probably last class I mentioned that Bell-Coleman cycle is actually reverse Brayton cycle. Brayton cycle we have discussed in the gas turbine. The same cycle, if we reverse the direction, then it will become air refrigeration cycle. Gas turbine we discussed the Brayton cycle is what? One compressor, one heater or combustion chamber, then one turbine. Turbine you can think of as a expander, and one heat rejection process. So the same processes will be there, but only the direction is reverse. That is why it is called reverse Brayton cycle. So the basic components are like this. There will be one compressor. Suppose the air enters into the compressor and it is compressed, and after compression it will go to the cooler. So the process 1-2 is taking place inside the compressor. So definitely the pressure and temperature will increase and volume will decrease. Then this high pressure, high temperature air is sent to the cooler, where some coolant, maybe water also, maybe air also, coolant is used to cool that high pressure, high temperature air. And after cooling, what will happen? Definitely we know what will happen. You also know, we will discuss it within a short time. So the process 2-3 is cooling process. Then it entered into the expander. So the expander is like turbine. Turbine expands something, but we call it expander in the refrigeration cycle. So due to the expansion, what happened? The pressure will decrease, volume will increase, and temperature will also decrease. So this process is 3-4 expansion process, and this low temperature, low pressure, high volume air enters into the refrigerator. This is the point of interest for us, refrigerator. So this is cooled air, and this air can absorb the heat from the refrigerator at low temperature. So after absorbing the heat, the pressure temperature will increase, and it will again enter into the compressor, and the cycle repeats. So we'll discuss one by one. So basically what is this? This is a compressor. So compressor, in the compressor air will enter. From where it will come? It will come from the refrigerator. After compression, pressure will increase, temperature will also increase, volume will decrease. So this is process 1-2. Entering into the compressor, going out of the compressor. So after compression, where it will go? It will go to the cooler. So definitely cooling arrangement will be there. For cooling, some fluid may be circulated for cooling. And this air, after cooling, the pressure is still high. Okay. If we cool one fluid, what happened? For pressure, volume, temperature, etc. Compressed air is cooled, so if we cool, that means temperature will decrease, and at the same time the volume will also decrease. Okay, so after cooling it will go to the expander. Cooling process is 2-3 and the expansion process is from 3 to 4. This takes place in the expander. So due to expansion, what will happen? Again the temperature will decrease, volume will increase, and pressure will decrease. So volume will increase, pressure decrease, temperature decrease. So what is the output from the expander? Low temperature, low pressure, high volume air. Now this low temperature, low pressure, high volume air can absorb heat, and it will absorb heat from the refrigerator. So this is process 4 again, and this refrigeration. So air will enter into the refrigerator, it will absorb the heat from the refrigerator and it will come out. So this process 4.1 is what? Refrigeration. So refrigeration is what? Basically absorbing the heat from the space, from the refrigerator unit. So this is heat absorbed from the refrigerator. And where is the heat rejected? In the cooler, heat is rejected from the system. And this is work done on the system because we have to run the compressor, that we will call WC, compressor work. And this will give some work output. Okay, because any expansion process gives us work output. So this is an expansion process. These are the processes happens in the cooler. Heat is rejected from the system. In the expander, work is received from the system. In the refrigerator, heat is absorbed from the system at low temperature. Remember, at low temperature heat is absorbed. And in the compressor, we have to run the compressor with the help of some power input. We have to give work to the system. That means work is done on the system. So, okay, this is the working principle of Bell-Coleman cycle, consisting of 4 components: compressor, cooler, expander and refrigerator. So let us analyze the system with these 4 components. So what are the processes? 1, 2, compression, 2, 3, cooling, 3, 4, expansion, 4, 1, this is heat absorbed, this is heat rejected. So if we consider a PV diagram, what are the processes we can explain with a PV diagram? So first we will start with the process 1, 2. So definitely process 1, 2 is compression process taking place in a compressor. Consider that the compression process is isentropic. So process 1, 2 is isentropic compression process. Okay, PV to the power gamma equal to C, reversible adiabatic compression process. So what happened in the cooler? Just now I have mentioned, due to the cooling, what will increase and what will decrease? What happened to the properties, particularly pressure, temperature and volume? Someone tell me?
The heat output. The volume will decrease.
Good. Volume will decrease because cooling decreases the volume. Very good. So in the PV diagram, what we can observe, that volume decreases. But at what pressure? At constant pressure, volume will decrease, because in the cooling there is no arrangement to decrease or increase the pressure. The pressure will remain same. So you look at the screen and you will see how it happens. From 2 to 3, volume decreases. Okay, from V2 to V3, volume decreases. And definitely in this process, what happened? Heat is rejected from the system. It will go out of the system. Okay. Now next is process 3, 4. What is that process? Someone tell me. Process 3, 4.
Isentropic expansion.
We'll consider that, assume that the expansion process is isentropic. So due to expansion, we know what is expansion process, and we all know how to draw an expansion curve in a PV diagram. So 3,4 is expansion process. Okay, this is expansion, and we assume that this is an isentropic expansion process. So due to expansion, what is happening? You can tell me pressure, temperature and volume. Volume is increasing, that is called expansion process. So next process is 4.1. Then 4.1 is what type of process? Heat absorbed at low temperature, and during this process also the pressure remain constant. At low pressure, low temperature, heat is absorbed, and because of the absorption of heat at constant pressure, and volume will increase. So 4.1 is this process. Constant pressure, we can write here that this is P equal to C, this is P equal to C, and this is also a isentropic process, expansion process. Now you look at the TS diagram. So same process will represent in a TS diagram. Say process 1, 2 is what type of process? You have already said, then this is an isentropic compression. So in the TS diagram, we can see the entropy remain constant. That means isoentropy process. You see process 1, 2 is isentropic process. From PV diagram we can see it is a compression process. From TS diagram we can see this is an isentropic process 1, 2. Now process 2, 3, from PV diagram we can see this is a constant pressure process, and because of this process this pressure remains same and volume decreases. Yes, volume decreases. You see how it happened. So in the TS diagram we cannot see any effect on volume. What we can see, you see process 2, 3. What we can see from the TS diagram, what is decreasing? Temperature is decreasing. Because why temperature is decreasing at 2, 3 process? Because it is rejecting heat rejection process in the cooler. Okay, then 3, 4 you see is again an expansion process. So you can write this is P equal to C, this is S equal to C, this is S equal to C, entropy constant. And 4.1 is again at low pressure, it is absorbing the heat from the refrigerator. That is why if it absorbs the heat, the temperature will increase from T4 to T1. Now you see what happened to pressure and volume in the PV diagram. Okay, you just see. So in the process, volume decreases from V1 to V2 during the process 1, 2. Again from 2 to 3, it is a cooling process. That is why volume decreases from V2 to V3. Decrease in volume. 3, 4 is expansion process. That is why volume is decreasing. Okay, this is from V4. That is about volume. And now you see what happened to pressures in the PV diagram. So pressure, what happened during the process 1, 2, pressure increases from P1, which is also equal to P4, to P2. During the process 2, 3, pressure remain constant, so P2 equal to P3. During the process 3, 4, pressure decreases from P3 to P4, and this way the pressure and volume changes during this whole cycle. Now come to the TS diagram. You just look at the TS diagram, how temperature and entropy changes. Process 1, 2, S1 is equal to S2, isentropic process. Process 2, 3, entropy changes from S2 to S3, and during this process 1, 2, temperature increases from T1 to 2. And again during the process 2, 3, temperature decreases from T2 to T3. Now come to the process 3, 4. 3, 4 is S3 is equal to S4. And during this process temperature decreases from T3 to T4. Again 4 to 1, entropy increases and it absorbs the heat at low temperature, and that is why the temperature increases from T4 to T1 again. Okay, these are the processes in Bell-Coleman or air refrigeration cycle. So I think you can explain the processes 1, 2, 2, 3, 3, 4 like this. Okay. During the process, heat absorbed is, we will represent it QA, and this takes place at during the process 4-1. What is the process 4-1? You look at the TS or PV diagram. This is low pressure, low temperature. At low temperature, it absorbs heat from the refrigerator, and that is the main aim. To do the refrigeration, we have to absorb heat at low temperature. Now what will be the heat absorbed? Q41. Anybody? What type of process? 4-1 you see. 4-1 you can see this is constant pressure process, P equal to C. And in the PV diagram you can say P4 equal to P1. So what is that? M, mass of say air, Cp, specific heat capacity of air at constant pressure, into temperature difference. What is the difference of temperature? From T4 to T1. So difference is T1 minus T4. Okay, this is the heat absorbed. This is the refrigerating effect. This is also called the refrigerating effect. This is the cause which keep the room cool, keep the space cool. Now come to the whole cycle. In this cycle you can see this is heat absorbed, QA, and this process is heat rejected, QR. So next we will discuss the heat rejected. What is heat rejected? QR equal to, during the process 2, 3. So it will be what? This is also constant pressure process. P3 equal to P2. This is P equal to C. So it is again equal to M Cp. Temperature difference how much? Higher temperature minus lower temperature, T2 minus T3. Okay. In the gas turbine we discussed that work done by the system was heat supplied minus heat rejected. But in the refrigeration cycle, we are going to find out work done on the system. So that we will call the compressor work. So what will be the compressor work? That is equal to heat rejected minus heat absorbed. Okay, it should be heat rejected minus heat absorbed. Okay, so work done on the cycle is heat rejected. WC is heat rejected minus heat absorbed. So what will be the heat rejected minus heat absorbed? That we will see. So that means this minus this. QA, heat absorbed, is MCP, this much. And similarly for heat rejection, it is MCP T2 minus T3. Okay. Heat rejected minus heat absorbed, that is MCP T2 minus T3 minus MCP T1 minus T4. Okay. So for refrigeration, coefficient of performance for refrigerating unit, it is not the performance parameter is coefficient of performance, that we call COP. What is the COP? Definition of COP we discussed in the 4th semester in the thermodynamics. It is the refrigerating effect, or we can say heat absorbed divided by the cost. What is the cost? The compressor work is the cost. At the cost of compressor work, we add we can absorb heat from a low temperature region and we can reject the heat in a high temperature surrounding. So what is QA in this? What is the QA? So in all this case, we can cancel MCP because everywhere MCP is common. So we can write QA is MCP will be there, but ultimately it will be cancelled. T1 minus T4. Then QR minus QA, what is that? Compressor or T2 minus T3 minus T1 minus T4. Okay. Now if we divide by T1 minus T4, then what we will get? So if we divide this by T1 minus T4, that will be 1. That will be 1. And below it will be T2 minus T3 divided by T1 minus T4. And minus again, if we divide it, it will be 1. So finally we get COP of refrigerating unit is this much. Okay, we can take some common also. 1 divided by, if we take common say T3, it will be T2 divided by T3 minus 1. And if we take common T4, it will be T1 divided by T4 minus 1 and again minus 1. Simplify this thing. Actually this is the formula for COP, but we can simplify this even more, and for that we have to apply the isentropic law, and that law can be applied only during two processes that obeys the isentropic law. PV to the power gamma equal to C, and that is process 1-2 compression and process 3-4 expansion. Okay. Isentropic law. First apply the isentropic law to the process 1-2. So if we apply the law to the process 1-2, then can you tell me what is the law? T2 divided by T1 equal to P2 divided by P1 whole to the power gamma minus 1 by gamma. These things we have discussed in the gas turbine. Okay, this is the law. This is actually combination from PV to the power gamma equal to constant and PV equal to constant. From that two laws we can derive this law for isentropic process only. So we get T2 is equal to how much? T1 P2 by P1. This we will call RP. In the gas turbine also we called it RP. P2 by P1 is RP is pressure ratio to the power gamma minus 1 by gamma. So RP is pressure ratio, and for process 1-2 it is RP equal to P2 by P1, and for process 3-4 also it is equal to P3 by P4. That means both are same. P2 by P1 is equal to P3 by P4. So we have find out T2 equal to this much. The process 3-4. What is the process 3-4? Now process 3-4 is also a isentropic process. So if we apply the same law, that means that will be T3 divided by T4 is equal to P3 divided by P4 all to the power gamma minus 1 divided by gamma. Now just now we have said that P3 by P2 equal to actually P2 by P1, and that is equal to RP to the power gamma minus 1 by gamma. So from this we can find out, we can write T3 is equal to T4 into RP to the power gamma minus 1 by gamma. You see, what is this? T2 by T1 equal to RP to the power gamma minus 1. Again, T3 divided by T4 is also Rp to the power gamma minus. So from these two equations we can write T2 divided by T1 is equal to T3 divided by T4. Okay? And from this we can get T2 divided by T3 is equal to T1 divided by T4. Fine, just rearrange the thing, and this you see these two terms, okay, same. That means T2 divided by T3 and T1 divided by T4 are same. So what we can get, this term will cancel. So what remains? COP will be 1 divided by T3 divided by T4 minus 1. So what we get, COP equal to this much, and finally we get this is equal to 1 divided by T3 divided by T4 minus 1. Okay. Now you see T3 divided by T4. What we can write?
So T2 by T1.
T2 by T1, but this we will write. What is this? P3 by P4 to the power gamma minus 1. And what is this? This is Rp to the power gamma minus 1 by gamma. So that we will write 1 divided by Rp to the power gamma minus 1 by gamma minus 1. So this is the formula, final formula for COP, coefficient of performance of refrigerating unit working on Bell-Coleman cycle. And what is Rp? Rp is equal to high pressure divided by low pressure ratio. So Bell-Coleman cycle or air refrigeration system, COP is equal to what? We got 1 divided by Rp to the power gamma minus 1 by gamma minus 1, where Rp is equal to pressure ratio. That is in our diagram, in the PV diagram, you can see that is equal to P2 divided by P1. That is also equal to P3 divided by P4. And P2 is equal to P3. This is the highest pressure. Whole cycle, in the whole cycle, this is the highest pressure. And P1 equal to P4, that is the lowest pressure. And this way, the Bell-Coleman cycle or air refrigeration cycle works. In terms of temperature also, we can write 1 divided by T3 divided by T4 minus 1. That way also we can write the formula.